Hi. So, some admin thing, just we'll finish the topic 6, dynamic games of complete immersion today, and then I'll release the assignment 3, which you should try to solve some games, which should not be very difficult. And just next Tuesday, probably I will not be able to come back for class because I will be in Beijing for a conference. And I look at the cases in the morning. The flight will arrive at say 11 or 12. Then I worry that I may be late. So maybe we will do the makeup class maybe after the semester is over. That would be like optional. So I probably cover something that is more advanced. So you can attend by Zoom or you don't have to attend. Something like more advanced topic. So maybe covering some bargaining theory, some context, some other advanced stuff. So I think our test exam will be focused on the first 8 topics. The remaining things that will be in advance if I cover faster than before. So don't worry if you miss or what. But I put the announcement on the web, and then the makeup will be done later when we have time. Maybe cover something experimental economics or behavior economics in those makeup classes, which is optional because not everyone want to do those, right? So that would be the thing. I'll make the announcement on the blackboard where I don't want to rush. So maybe I just skip the next class. Then we'll make up somehow afterward by the time. So let us get started. Just to remind you a little bit about what we have done, because I think it's a week ago. So probably it's good to briefly review what we have done. Okay. So just dynamic complete information. I guess this is the game that you will use most of the time in practice. If you want to ever try to do game theory, and then this is likely beside the static games, this is the one that use most often. Because usually you would consider multi-stage game, right? Either you have upstream firm, downstream firm, right? They move in different timing, or you consider over time, right? They are repeated interaction. Or look at the financial market, accounting market, where investor or firm, they would move at different time, one time. So it's very common that not everyone move at the same time. One of the reasons that why you want to have a dynamic game is because of solving everything at once can be difficult, or can be too many equilibria. By separating them into one by one, right? Do a backward induction, you must have some solution. If that makes sense to you, right? That would explain why, right? Because you ask why you have supply chain, why don't all firms move at the same time, right? That would be also an easy way. But you can see in the real world, right? Supply chain, usually the upstream one will move before the downstream. That is not unusual. So I hope that would be kind of okay. So we describe how to represent a dynamic game of combination is this graph, and this graph tells us everything, right? Who are the player set, right? Who are the action, what are the history, what are the payoff, or the player funds, and so on and so forth. Everything is well defined from a tree. So that's why you always define by tree, right? Of course, if you are not going to draw a tree, then probably you have to make sure that the reason why we need this kind of thing is because when you write a model, when you write the written part, make sure that all the description can be found unambiguously from your test, right? Although I rarely say anyone actually really define it, but you make sure that your description is well defined, right? You have to specify, remember, what are the payoff for all possible history, right? Sometimes you are tempted not to define everything carefully, right? So this is the part that I want to mention, because when you write tests, you have to make sure that you don't miss those, okay? And the solution concept is much stronger. We'll use the called sub-game perfect equilibrium, or sub-game perfect Nash equilibrium, which is by saying that if you can decompose the game into multiple subgames, you want to find natural equilibrium in all the games. At the intersection of the equilibrium in all games, it will be the subgame perfect natural equilibrium, right? Just require if this is a natural equilibrium the whole game and also natural equilibrium every subgame. And usually you can solve by solving backward induction. That is, but do note that backward induction only apply where the game is finite, right? The finite, if the game is infinite, then this subgame perfect still defined, but the backward induction is not well defined, right? Because you cannot start from the end. So that's why there's a substantial difference, right? With the finite, they're the same, right? So that's the thing you learn in operation research is you can look at the last period and go back, but you can't do it, right? Especially you can see from the repeated game, right? The infinite game, you cannot really do it. Okay, you have to specify all possible subgame, which can be very difficult. So, and also we talk about if you allow simultaneous move, right? Then in this kind of representation, you allow the idea same as what we covered in the previous topic, which is simultaneous move game, right? Because player 2 doesn't know where he is. I mean, doesn't know where player 1 have chosen, right? So it simply means that, in fact, static game is not really static. Right? Static game actually extends the idea that as long as player 2 has no information how player 1 has chosen, then the same, right? The static game is not static. Just player 1 doesn't know player 2, player 1. As long as they make the decision by their own, right? Then that will be the same. So it's not static. It's actually more general than we thought, right? As long as, right, even though we make sequential decision, as long as it's people in the darkness, then it's still simultaneous move game. Let's consider a case where a firm try to hire workers, right? If there are multiple firms are sending offers, and even though they send offer in different timing, as long as when they send offer, they don't know the other firm is making offer, right? Then it's still considered simultaneous move. Same as the firm, right? When firm making pricing decision, right? Maybe some firm release the price earlier or whatever, but if the organizational inertia is such that price changing is not that easy, right? There's a standard procedure of how things being decided, right? Even though they announce price sequentially, it is possible that it can consider as a simultaneous move game, right? So that would be the case. Okay. So I guess this is the very common and famous game which you will use a lot of time. It's called stable game. Stable game is basically one firm is a leader who decide first, the others are followers. Okay. And of course, you can allow multiple leaders and multiple followers. That we find there's no problem in this framework, right? Just solve backward induction, right? You would do it second stage, with follower, they move, and then the first stage, the first mover move. Okay, so the leaders can move first, and the follower will move later. Okay, so this would be the this kind of model can be very useful. And we learn how to define those. I don't want to repeat that. And the game, and the main solution or the main issue is basically precision dynamic, right? Because these games usually is very complicated. So you look at the literature of the book is most of the time people would focus on precision dynamic to understand what's going on, because if that works, can generalize. So precision dynamic is always the worst case scenario, right? Because in the one period game, it's always natural equilibrium, dominant solvable, the worst case scenario, right? But the problem is they are not cooperative, right? So we want to have a case where C if is able to generate cooperation when you allow multiple interaction. And we know that when there's a finite period, it can't work, right? No matter how you change it, right? And infinite period, it can work if players are patient. Or you can change the game, right? You allow multiple equilibria, right? Then you work, right? So only if you allow the single stage game like this, right? In that case, if you have finite period, it still work, right? So basically just telling you a story, right? If you're able to create new opportunity, right? Look for new thing, new option, then that will work, right? Even though the new option need not be better than the CC, right? B.B. is not better than CC, the outcome, right? It's not Pareto superior, but you can create something that can agree upon, which is Nash equilibrium stage game. You can do something good, right? So in order to support a outcome, let's suppose you consider the climate agreement, which they do the great thing right here, and this is they are selfish, right? In order to support something, it's not Nash equilibrium. It need not come up with an agreement such that they would be able to achieve the best, right? At least you can come up with something that is better than the worst case scenario, then you can support something that is not there. So that gives you some idea, right? Why when you talk about international agreement, they need not be efficient, right? But they can be served as the benchmark or the punishment or the reward so that you can lead to a better outcome. So that would be the moral from this exercise, okay? And here we have formal definition of finite game and infinite game, right? Finite game is something no talk to solve, Bell induction, right? And if infinite game, then the problem is once you have infinite game, then when people are patient, then any outcome is possible. So basically, this is a negative result because more or less is what we call Bohr theorem, that everything is possible. Then the theory is useless, right? If I predict everything is possible, then there's no theory, right? Because that is the idea of what we call the Karl Popper or the positivism, right? So you want your theory to reject, right? If your theory is not falsifiable, right? That's a problem, right? There's nothing from experiment you can reject, right? Suppose consider experiment of with the game, right? Then any experiment outcome is compatible, right? Then your experiment is useless, right? Because everything can be explained by invoking, say, people are super patient, right? So that would be something that is challenging, okay, to handle. And of course, we don't cover here is one thing that people in the literature working on is against the Fock theorem is what we call we have a very sophisticated agent where he can keep track of everything, and also he can observe what other people have done. Right? Later we will see when we drop this assumption, things become very different, right? Especially when we talk about pollution in the price, right? Or the OPEC, right? You know, every one of us in this room maybe collude, right? In the exam, maybe you guys are not doing anything in the exam. Everyone submit me a blank sheet of paper for your final exam. Then either I have two choices, either I fail everyone or I give A to everyone, right? And that would be a difficult choice, right? And probably I may be forced to give good grade to everyone in that case, when we look at other score, right? But the problem is you may not know may not be sustainable, right? Because your friends you may tempt to actually do something which may not be detectable, right? Just like the OPEC, right? Maybe they agree on not to produce that much, right? But you don't know actually the guy actually badly, privately send the oil to somewhere to sell, right? Then you can really beat it, right? So that is an issue. You cannot easily observe. That is a problem. But let us continue the definition. This is an important definition. Same as Nash equilibrium. Okay, you would just ask if you change the strategy, would you need to would you regain? And turn out that we only need to check along the equilibrium path, proposed equilibrium path, would any player have incentive to deviate, right? At every point of time, right? Because that is the idea of what we call the one-step deviation principle. We only need to check only one particular move. Okay, that would be something, that idea. Okay, and the subgame perfect Nash equilibrium have to check all possible history. Okay, that is something different. for every possible history that's considerable, not only in this or not only in the game that appear. Okay, let me show you this example here is I think we have that already to check, right? Why we have to look at this percent dilemma, right? The strategy is you have been CC, then you do CC, if not, you do DD, right? So Nash equilibrium is simply checking, holding other guys constant, right? The strategy, right? If the other guy has been CC all the time, right? So would you have incentive to deviate, right? And the answer is no, right? Because you're patient enough, then you deviate just a gain of 5 and 1 forever, right? Otherwise than 4, right? So that's why you won't deviate, right? Because that is to check on the equilibrium every period the same, right? Suppose in the first period, you only check whether this is better than that, right? Second period same. So every single period along the path, you need to check, right? But the subgame perfect Nash equilibrium is different. It's a check, right? Once you deviate, right? There's a history that is other than that. That is, this part is the subgame perfect equilibrium, right? Suppose you deviate in the first period, okay? And according to the rule, you pay DD, right? And do you want to deviate? The answer is no, right? Because this is dominant solvable, right? In that case, is no one want to deviate because other guys only pay D, right? So this is the part you have to check is different from the say SPN. So I think I covered this example already, which is a nice example. Probably it's good to see this part because Fog film already tell you this outcome, right? Although I said this is the best outcome, right? But there can be anything, right? Because when delta is sufficient patient, it's not just this collusion outcome. Anything is possible, right? But we focus on the case if it's firm optimal, right? In the case that's symmetric, they focus on the frontier, right? There can be anything that can be supported, okay? They need not equally split this QM over 2, right? Need not be equally split. Okay. If they're infinite patient, very patient, it can be one guy getting a large chunk of that, the other guy get a smaller chunk. Okay, as long as this is bigger than the Nash equilibrium payoff. Okay, so that is something that I didn't show you, but you should know that this is not the only outcome, but this is the natural outcome we look at, right? Because there's a huge number of outcomes that is available there. Is that okay? Is that okay for this one? I guess. So now I think this is technical, but I want to show you this one because some of you said my class is too easy. So let's come up with something a little bit more fun. This is the game actually this example in a econometric paper, which actually can be generalized to a much more general Fog theorem. Right? The Fog theorem is said is anything better than Nash equilibrium can be supported if you're patient enough. The reason is if you don't follow what we propose, then we go back to Nash forever. Right? So this is the model that allow you to go even better than that. Okay, need not be Nash. That's what you will see. Okay, the idea is following. Look at this game. We have free action for each agent is symmetric. Right? You can see number are symmetric, and you can easily check that the only station equilibrium is MM. They produce a median level, middle level of production. Low is low, high is high. It's common game, right? Okay, this 7, player 1 don't want to go up or down, right? And 2 don't want to go left or right. So 7 is the only Nash equilibrium. You can check. Yeah, so question. Okay. So if you want to support this, which is a Pareto superior, but there's not Nash equilibrium, okay? Then if you want to use the idea of the trigger strategy, which means that we will do L and L, if not, then M forever, right? Just consider percent dilemma. This is the case, right? This is either, then go to this, okay? So that would means that if you stick to the Nash equilibrium, that's what you get. If you deviate, you get 15 for once, and then you get 7 forever, right? So as long as your delta is high enough, then you would get support. Is that okay for this one? According to equilibrium, you get 10 forever. If you deviate, you gain 15 for once and 7 forever. Okay, because 7 and 7 is a natural equilibrium. Is that okay? Is that okay with this one? LL, yeah. It's like person dynamic. Everyone choose L if it's with LL. Right? That's what we mean by trigger strategy. Trigger strategy means that we will start with LL if nothing has been done, okay? Or if parts have been LL, we continue to do LL. If that has something is other than LL, we will go to MM. And why this is a subgap perfect? Because under MM is always MM, there's no problem, right? Because it's natural equilibrium by itself. And if you start with LL, you deviate, the best case is M, right? You deviate this one. So that's the gain, but you end up with 7 forever. So as long as you're patient enough, this is something can be supportable. Is that clear? Right? You can forget about H. There's no need to worry about that part, right? Because we talk about subgap perfect natural equilibrium, this one. Okay. And now the thing is, this one, yeah, we can consider a little bit more complicated. It's called the penal code. That is very smart. Later you will see. The thing is, the main idea is the trigger strategy is punishing the one who has been a good guy, right? Because remember this case. Look at this one. Look at this one, right? So player 2, if player 2 is a good guy, he has good here, he 10, right? He get bad, he gets 3 and 7, right? So actually it's not so good for player 2, right? And so, and also player 1 is, no matter what they do, is also get the same, right? So that's the idea here. A rule that he proposes, you have to decide that each player would have its punishment scheme. Okay, it's not punishing them together. So here is A star would be the proposed path if no one deviates. So there's a book saying that, okay, if everyone follow, we'll follow the A star. Okay, if someone have been bad, okay, say player 1 is naughty, okay, look at the naughty book. If naughty, we start this one. Okay, if player 2 is naughty, we go here. Okay, and whoever doesn't follow the thing, that will get punished. Okay, suppose everyone go to here, that's no problem, things go on as usual. If player 1 is naughty, okay, player 1 plays something else. Okay, and then we'll come to here, we should play this one. Okay, and everyone has to follow this procedure. If say player 1 here don't follow this one, so we start the punishment again. If along this punishment player 2 doesn't follow, we'll go to player 2's. Okay, and you don't need to worry about simultaneously they deviate, because that is not natural. You need to check for the natural equilibrium, right? You need to deviate. Okay, so that would be a little bit complicated, right? Because whoever deviate, right, then we'll start his punishment, right? If you don't want to follow through the punishment, we'll punish you from the beginning. Okay, look at MH. What is that? Okay. If player 1 deviate, we go to MH. Why? MH is the most horrible thing that player 1 can conceive, which is -4. Right? If you can try to see the case if player 1 deviate, I will just force you to have this guy. Okay. Later you will see why this guy would happen here. Okay. And once here, then it will be going to LM. Okay. Which means that, okay, you will get back to here. Okay. If player 1 deviate to here, suppose, he'll get to this guy next round, and then here, which is benefiting player 2, right? So you can see we have to reward player 2 somehow. Okay. So let's see why this is a little bit lower. So it has to be different. Okay. So let's see, this is a little bit interesting thing goes on. Why is that the case? So overall, okay, check is whether they can be done. This is what I said, okay. But let's do the proof. This is what I just said already. So we will see lower, but the bound are lower. Okay. So how can we support this one? Okay. So if you follow 10 forever, you don't follow, you deviate, you get 15. You get -4 and 3 forever. So remember we said the code is MH, LM, LM, right? So if you deviate, you earn this one, then you earn this guy, and this forever. Okay. So that would be the punishment. Okay. Instead of going to LL, right? Going to MM, which is very good. Right? I want to make it less. Okay. At the same time, I want to punish, or I want to benefit the guy number 2, right? Okay, so that would be the idea. Okay. Of course, you will ask how we decide this punishment. Later you will see. Okay. But the main idea is that you would have a player-specific punishment. That's the main idea. Okay. Once you see this, you will see this is easy because you punish more, then you allow much better range. Okay, there's no problem. You reduce much more. So that is not a big concern here. Okay. But now we have to make sure that, okay, player 1 don't want to deviate from the punishment. Okay. So under this punishment, okay, with MH and LM, right? Under punishment is like this. So in the punishment, we're here. Right. Sorry. Look at this is MH. Right. He will get -3. Right. So he will get -4 and 3, right? So along the punishment, we start the punishment. He will getting 4, -4, 3, right? Forever. Right? -4 and 3 forever. Okay. That would be along his punishment. So the question is, can he actually jump to here? Right? He did not follow a punishment, right? He can say, okay, I'm not going to choose M, I choose L. Right? But if you deviate from this one, we will punish you again, right? So you can run away from punishment. But you run from punishment, you will get punished again and go forever. Okay. So that's why the idea is like this. You get -4 and 3 forever. But if you don't want to follow a punishment, you escape a punishment. You restart the punishment again. Okay. So we make sure that you don't want to escape. Right? You want to escape. So that require actually delta pretty big. Okay. And we also need for player 2 to follow through the punishment, right? So that's why we have to make sure that if he actually follow through the punishment, there's something, because we are not following the Nash, right? We'll make sure that this and 15 is more than, okay? He go back to the Nash and then get punished by the same, right? Because this is the punishment for player 2, right? Which is symmetric. Right? So that's let me go back to here to make sure you understand, right? Because if player 1 deviate, right, which we will get to this guy and this guy forever, right? And suppose player 1 don't want to follow that, he jump to here, right? Because that is player 1 jump, right? But then according to the rule, if he deviate once, he will got this and this forever. So you want the blue one is better than the orange one. Okay. But you also require that player 2 also the same, right? Because player 2 will be also the same, right? He will be looking at 5 and 15 forever, right? But if he deviate, okay, if he deviate, what will happen to him, right? If you deviate under the deviation, what can you do is he jump to M, right? Because player 1 is using M under the punishment. So if he deviate, it will be 5, 7, right? Because it will be 7, right? With deviate will be 7, right? But once he deviate, he will start getting punished. Will be -4, all right? And the 3 forever, right? So because that will be punishment will be in this manner, right? Is HM and ML, right? So this player 2 punishment. So you want that to happen. Okay. So that is how we get this one, right? You get -4 and 3 forever. Okay. So that's not difficult to see, it's okay, because you get a lot, right? So that's just fine. Okay. So now we have to check other thing is, if you get 3 during the second phase of punishment, do you want to deviate again? Right? What is, remember, the punishment is, remember the idea is, right? The punishment along is this and this forever, right? This punishment for player 1. So now we're undergoing the second stage of punishment here, right? Is it the case player 1 will deviate, right? Okay, about this, we're here already, right? Because of game purpose. Check whether 3 forever is better than you jump to here, you get punished again, right? That'll be cycle. So you have to check for every stage there will be so that's why you have this guy, right? 3 forever, you jump to there, got 4 with 7, but you get punishment again. Okay, so this is second stage of punishment for player 1, and player 1 want to deviate or not. Okay, but player 2 don't want to deviate because player 2 already given 15, right? At that punishment, then what do you get the best? So you don't need to check, right? Because 15 is already bad. So what did B.B.A do? So that's only, this is the requirement. And therefore you combine everything. 7/4 is the lower bound. So it's much lower. Okay. So that is the main idea, right? So, and so the question is, oh, this is a nice result, right? Because Nash reversion is not the best, right? The Nash reversion means we can support something that is even more crazy, right? We don't need the Nash as long as we have something complicated. Okay. And actually, this idea can be generalized to a very famous result. Predictable masking in there, I think the most crazier one is this. Okay. Is the result we call the min max utility is what it said is what you can guarantee no matter what other people do. Okay, so look at this. Look at what's the min max level. The minimum you can ensure no matter what other people do. Okay, so look at this one. So remember the formula. Let's go back to min max formula. You will be maximizing yourself first and minimize based on other. Okay, so given other people's strategy, okay, what is the max? 15, 7, 0. Right? For every strategy, other you have player 1 with the maximum is either 15.7 or 0. And minimum of this will be 0. So for player 1, he can always guarantee to get 0. You can you can't. Why? Because you can't really force him to be lower than 0. Why? Because he can always choose L, right? He can guarantee that it's 0 for him, right? No matter what. So that 0 is guaranteed. Same 0 for player firm 2. So that means that as long as the equilibrium payoff no less than 0, then it can be support. Is that clear? So this 0 is called the restoration payoff. It's the minimum they can guarantee. Okay. And in this case, we are saying that, I mean, of course, this is a very technical result, but that is any payoff greater than, strictly greater. Okay. Any greater than 0, that's fine. So it's 0.1, then will be supported. Okay. So anything that give them any equilibrium outcome, as long as more than strictly, okay. If your delta big enough, then it can support. So that is people will say the negative result, right? Because almost everything can be, as long as you're not stupid, then everything is done, right? Because you can always guarantee something, right? As long as you can hide the guarantee, then it's there. But so that's why you look at the subsequent literature, we try to relax a lot of assumption there, okay? But later you will see what we are relaxing. Okay, so that is the result for the Fock theorem. So next is we want to give you the application of repeated game in the price coordination. And that part we will talk about 2 sections. One is called perfect monitoring, which is something we have done already. The other one will give you some taste for what we call imperfect monitoring, which is something that is in the recent research. Okay, recent, I mean last 20 years. But unfortunately, this literature is pretty slow, so it's not something that it's already technical as well. But we touch some important application, and you will see there's a lot of things to be done, and it's still the literature is still not fully done yet. There's a lot of open question there. So if you are a game theorist, you want to do some crazy technical thing, this is thing you can do, and there's a lot of application there because I think with the game applies to many things, and then later you will see what is so complicated there. So I think it's good to start with often you see this paper, the macro paper, I mean say in AR paper, which come up with something very counterintuitive, okay? Which actually try to understand the counter-cyclicality of the price, which you will see price in a good time is lower than the price in a bad time. So that is where because you expect, right? In understanding general thing is the market is good, the price is higher. The market is bad, the price is lower, right? So this is trying to show you that it's possible in repeated game because repeated game allow you anything, right? So that is something that you will see in this model. There's something funny. Okay, let's see the model. So in this framework, consumer the demand is determined by the nature. It can be high or low, and it's observable, right? People know it's good time or bad time. Okay, and good time, bad time has random probability, 1 minus W and W. Okay, and it's IID. Okay, just make things easier. And consumer to pay is 1. Okay, everyone to pay at most $1 for the product. As long as below $1 they will buy. Okay, I think that is simplest you can imagine. Okay, so there are 2 firms in the market. Just make sure that they're Bertrand. Okay, and the price is saying they split the market equally. If one is lower, then the firm that lowered the price will get every consumer, and if your price higher than the guy, you get 0. So standard Bertrand, right? And then the history will be all the price history, or the quantity sold history, right? This is the history. And the strategy would be depend on the history, also today's demand, right? High or low, right? That will map to a number, right? Which is the price you want to charge, right? You set the price. So now here we claim something which I said is very counterintuitive. Okay. You will see, okay, the strategy where two firms the same price, such that if they're patient enough, okay, of course they can support something nice, right? No matter good economy, bad economy, of course they will charge the same price one, right? You charge because the price is they're going to pay $1, charge $1, right? That's fine, right? If they're patient enough, they can support collusion, right? Because Bertrand in one period should get zero price, right? There's no marginal cost here, right? So we just expect that. But he said, not surprisingly, if they're patient enough, you can see the collude, right? They charge a monopoly price, right? If you're monopoly, you charge one, right? Now, of course, not surprisingly, if they're not patient enough, they will enter the Bertrand, which they charge zero price, right? Because they compete, right? Because they're impatient, right? They don't care about the future. You care about today's, then everyone undercut, right? Then undercut, then go to zero. That's Bertrand. The Bertrand, one period gain, marginal cost is zero, then you always, at the end of the day, per period is just zero. To get that, right? So here we have two outcomes that is reasonable, right? Already, right? So if firms are not patient, they only end up in something percent dilemma, right? If they're patient enough, then you will get something nice, right? That's okay. Now the question is somewhat what happened when it's intermediate, okay, which is probably something that we care, right? And turn out that, well, surprisingly, when it's low, it's 1. When demand is high, you charge a lot less than 1. So in good time, you have lower price. Okay, of course, they argue that this is a price war, right? In a bad time, they don't compete. When a good time, they lower the price. Okay, of course, we try to explain the intuition behind, but that is the result they try to prove. Okay, is that clear? The idea, what we're trying to do. Okay, of course, they only characterize there as an equilibrium. Of course, there are many equilibrium is possible, but they try to show you equilibrium where it is possible that good time the price is lower than bad time. Okay, so that is the idea. Okay, that is a possible, right? It may not be surprising to you, but this result actually get them AR, right? So I think it's surprising, right? At least you don't think that is possible, right? At least you don't think that is something that is reasonable. Okay. So you can look at this. This is the idea. Okay. When the discount factor is low enough, that is something here. When discount is high here. When it's intermediate, bad time, low high price, good time like this. Okay. As patient goes up, then actually converts to this one. Okay. And when here we will go to the ratio. Okay. Of course, you can see if this is very close, QH is very similar, then it will be this gap is getting smaller, so everything makes sense, right? Because QL is getting higher to QH, then the red will shift very close to the blue one. Okay, but let's see how and why this is true. Okay, and then we'll explain the intuition behind. Maybe let me finish the slide before break, because otherwise that will make us things are more continuous. Okay. So do note that we can have a trigger strategy, right? Which means that if everyone don't follow what's supposed to be done, we will Bertrand forever, right? So we're done, right? So that would be proving that, okay? So we want to see whether we can sustain QH, okay? If we follow what we're supposed to do under QH, we get this, right? Half of the profit, we charge the same price, okay? If QL, we get this one, okay? And now look at this particular guy. Okay, this is slightly little bit more complicated. Okay, if you deviate, you get whole market for one period, for the rest will be zero, right? But if you follow through, what you get? What you will get is under W probability, it's good time in the next period, which you get half of it. If it's a bad time, you get split this, okay? And this will be done forever. Is that clear? Okay, let me repeat. This looks a little bit clumsy, okay? The right-hand side is easy because right-hand side means I deviate, I get the whole market, but I get zero for the rest of my life because the trigger strategy, right? So anyone deviate, we go to Bertrand forever. The next reversion. So we get this guy and zero forever. So that's what I do, right? If you along the equilibrium, you split the market, right? And next period depend on the nature. If good, you get this. If bad, you get this, right? Because IID. So what continue is all the same. Either you get this or that, this or that every period. So that's why you can write in this way, right? So every period, the expected payoff is the same, right? According to the outcome, right? So that's why you have this, right? It's nothing deep here. Okay. So if you rewrite this big delta on the left-hand side, right? You have this guy. Okay. And you can see the only relevant part is which one? This one, right? So this one, right? The higher one. Right? So this is the guy. So that's why you get the delta. Okay. So you get it, you plug 1, 1, 1 there, you get this guy. That's the delta, right? To put 1, 1, 1 here, right? 1, 1, 1 here. You get this threshold. Okay. And now the next part is to show you, okay, why we have QL less than QH. Why is the case? Let me think why we have that. We can solve the threshold, that's fine. Oh, okay. I see. I can see why is the case. So what is left is to show you why we want to have that, right? So okay. Look at this, right? We need this one to be less than 1, less than or equal to 1, right? So it would give you the QL is bigger than QH. But let me check why it's the case. I forget. I'll check out during the break. But we can look at the denominator and check y equal to, let me see. So this ratio and now I'll check this guy why is the case. But you can show that I forgot. And they will show you that the price under the low case must be less than the high one. And that's the reason why you would see that they argue. You will see usually is a high price, then there was some kind of aggressive competition. So that is what they're doing. But I'll try to answer the question after the break. I'll check out the answer. So after the break, we'll look at a little bit more complicated idea where you, in the previous case, the price is known. Okay, everyone know whether you cut the price or not. Okay, because you are looking at quantity, right? In that model, right? Okay, we can look at with the price reduction. But in this one, you can't really look at the state of the world. Okay, this is not observable. Okay, you can't see whether the economy is good or bad. And in that case, you are not entirely sure whether the other guy have defect or not. Okay, you have some idea that might or might not be. So that would be the main idea. Okay, so let's break for 15 minutes, and then maybe you can resume, take a rest. So I think now it's we'll resume at 39. I'll come back with the solution to why that's the case. Okay, let's break.白几只吧。
就是不能在这里产品
哦，对，不能这样。
那考试范围就是这个学期
对，就八个考试，8个专辑，
跟作业类
跟作业差不多。
哦，
好的。 Oh, got it. That's very simple.
那你不确定固态淡菜的标准是什么？
啊，你有两个 strategy 去 nature 决定是固态
如果是固态的话，那这个
，QH 等于 nature 决定你的
我
做带
我有点混了，就是如果它固态价格更低的话，那它不是 inferior。
它不是 income 是固定的，
就是 nature 里是不考虑
你
income 的。
得 pay no，你的 range pay 是 one， 但是有多少人愿意买是 varies，it's not about individual consumer。
哦，对
aggregate 上面
会
它可能你
measure
aggregate measure 的时候，它可以写说它是 inferior to it or so, but just more people can buy your product. Right. So I noticed we have Halloween. So feel free to get some if you want. You come to get some candy that make you stay awake. Just in case you worry about is toxic, I take my one. It's going not to be well, that's how you that is the game theory, right? That's why when the Western people you cheers is to make sure that my drink actually go to your one. They pong bay, right? Is to go to your one, then make sure that it's not toxic. Okay, so I take my own to make sure that you feel safe to pick what I like. Okay. So I guess I didn't explain this one. Actually, it's very simple, but I just somehow I miss it. So why we have this? Okay. I look at this one. Okay. This is what one support, right? This is the one strategy required this happen. So if our delta is very high, we can always put 1. There's no problem for this inequality to hold, right? So when it doesn't hold, that means the delta is small enough, and the right hand side is big. Okay. So remember now your PQH and PQL is big, is 1, right? You start with 1. This delta getting smaller, and something will get violated, right? But when you get violated, what happens is this number is smaller than this one, right? This one's smaller, this one's smaller. So which one get violated first? This one, right? Same denominator, the numerator, right? Because this is high. It's 1, 1, right? This is higher than this one. So how can you make sure this doesn't satisfy? The thing is to reduce this one, right? And to make this one lower, although it's higher, but this one's lower, and this one reduce, right? So that's why how you get the inequality satisfied is you reduce this guy, keep this guy, okay? And you still are making highest profit you can get. That's why I have that, right? You can still keep QL is 1, but you have to reduce in order to satisfy the delta inequality. Is that clear? Of course, if you're super confused, you can go back to AR paper, but I don't think they give more than I said. Maybe I should elaborate a little bit more, but the idea is like this, right? Because remember, if possible, of course, you have to satisfy this inequality. The best case scenario is 1, 1, 1, 1. That is fine, right? And if delta is so low, right, so bad, then you can't satisfy. Even this is 0, right? The only thing you can do is 0, right? So that's why you have that. They cannot satisfy that. But the thing is, look at this one. The first thing to cut is to cut this guy, right? Because they have same denominator, right? And obviously this is maybe should be more binary than this one. So the thing is to reduce this guy. Okay. So then this is how you get this inequality hole, right? So this one increase, of course, this one gets up, but as long as you will see this is the way to this guy, right? In fact, if you put in this number, and these two inequalities should be the same, right? That's how you get that number there. Okay. So that's how you get, because you want that both inequalities should be the same, right? You set the equal threshold, set this as 1, then you get QH, just P of QH. Okay? Is that okay? now we get to another paper. It's also a very famous paper. Actually, today we discussed two classical paper in the game. This is called the secret price cut. Okay, it's a Blue, Pierce, and Stachiti, and then they basically is a duopoly. Okay, again it's homogeneous good zero cost. Again, there's a world, but it's not use W, but alpha. But I just follow the text, follow the notation in the jet paper. So it's slightly different, but the same idea. The only different last bullet point, which said that the state of the world is not observable. Okay, so before is high and low, you can set the price. Now you're not allowed because it's not observable. You can't see it. Okay, you cannot see the state of the world. So in particular, what do we have? Look at the example. It's even easier. So demand curve is like this. Okay, as long as your price is less than 1, which is the willingness to pay is $1, right? As long as your price is less than 1, the 2 units of demand, right? The total number of consumers 2. Okay, and this make our life easier, right? And the function will be the following, right? Same price. If you can get 1, you have lower price, you get the whole market. Otherwise, get 0. Okay. And the best state of the world is very simple. It's just no profit and no demand. Okay, this is the simplest thing you can imagine, right? This, of course, you can generalize it. I think in the pretty easily. Okay, you see this 2 states of the world, right? 0 demand, 0 profit. When there's a good time, you can make some profit if you low price enough, right? So more or less present that really Bertrand thing, right? Okay, but you have a Bertrand thing with a bad state of the world. Okay, so you can see the only complication is like this. You can't really distinguish whether it's a bad state of the world or you're being cheated, right? In the bad state of the world, you can't observe state, but in the bad state of the world, you get 0 profit. If you and I collude at a certain price, right? We agree a certain price, we charge the same price, right? We earn some profit. But if I don't earn a profit, it can be due to the fact that you cut the price or the state of the world is bad. Okay, so that is the only complication, right? If we are making profit, that's no problem, right? We are sure that none of us is cheating. But if we see we have 0 profit, what can we do? What can we say? Right? Can we conclude something? Right? It's hard to say. We can't really observe what's going on there. Right? So that's an issue here, right? We can't really perfectly observe. That's called imperfect monitoring. Okay. So it's not you can't see with the bad, it's the bad state or the bad behavior from your competitor. So that's why you cannot do grim trigger. Why? If you do grim trigger, which means that you see the 0 profit, you punish, then you punish very quickly, right? Because there's a non-zero probability that you get bad outcome. If you see bad outcome, you punish, then they'll never collaborate, right? Knowing that no one would incentive to do anything, so that means that we cannot do grim trigger. That's a good thing, right? Because once we're gonna do grim trigger, so the fog theorem not so easy. Okay. So how can we collaborate? Okay, we will in the literature there are 2 types of in the imperfect modeling there will be usually 2 types of model. We focus on the one we call public signal. Okay, and there is another type of model we call private signal. Okay, public signal is that something that people can observe. Okay, and that's called the sunspot. Okay, which means that here is every firm can look at the sunspot. Okay, can observe his profit in a sunspot. Okay, and look at the sky. Okay, and the history is look at the sky, and the sky will be very useful. Okay, and that means that here maybe that's basically this is a random number, right? The sunspot is basically a random number from 0 to 1. And this random number will be very useful to consider when to put in punishment. The reason we see Grim trigger, the problem is if we always punish, then you can never sustain collaboration. So here the sunspot we will be using is we will do action based on some random event. You may punish or you may not punish because I don't know. So that is the main criteria. And you probably say, okay, why we do this? Indeed, there is an actual case in antitrust in actually how they collaborate. Is look at the moon, look at the temperature, the weather. That will be how they collaborate. Just like if today weather is good, I will forgive you. Weather is bad, then I punish. But later you see, okay? But the goal is this completely irrelevant thing can help us. Very surprising result because something like we will do punishment or action based on something completely irrelevant. It's like we toss a coin and decide whether we forgive you. If it's not entirely surprising, look at the history in our country or many culture. What we're going to do if we don't know what to do is to ask a witch, God, and toss a coin, right? Or burn something, decide whether you're guilty or not, or whether we forgive you or not, right? You notice a story, right? If you are going to cut people's head, right? If you cut the head 3 times, you can't cut, then you release, right? Then we forgive whatever. But I mean, there's somewhat like this, like we actually make decision based on some random thing, okay? So the equilibrium is the following. The structure is under collusion, we collude at price 1, which is the maximum we can charge, right? Because the maximum price is 1, right? If you charge more than 1, you don't get anything. If we get punishment, we go to the Bertrand, right? So this monopoly price, this is the Bertrand, right? So we go between them, and there will be some punishment period. So we will get we cannot get forever punishment, right? There will be finite punishment. We punish for a while, we will return. Okay, later you will see. And there will be sunspot. This will tell us that the die tell us whether you get forgiven. Okay, let's see what the structure is. The structure is rather complicated. Okay, but look at the first one. When you would collude, that's very simple. 1.1 is when the beginning of the game we collude. No doubt, that's the easiest. 1.2 is what? 1.2 is if we have been colluding, we continue to collude regardless of the sunspot, right? So the first 1.1.2 is very simple, right? The same as person dynamic. If we have been colluding, we continue to collude. In the beginning, we collude. Done, right? So 1.3 is slightly a little bit complicated. 1.3 said the following. So if the last period, I get nothing and no profit, okay? I don't know whether it's the other guy cheating or bad thing happened. I don't know. But what happened is if the sky is bright, which is X bigger than beta, okay? Or the God forgive him, okay? I told the con, the God said, okay, he's fine. I mean, he's not cheating. I mean, I don't know what it is, but there's we agree that. Everyone observed that, right? He told the con in a temple. It's okay. So we continue forget, okay? And so okay. This is the current period. Okay. And look at we already punished the guy for T period already. Okay, we have been not collaborating for T period. Okay, then we forget. Okay, we have limited memory. So if we have been punished for T period, we start fresh. Okay, we cannot punish forever, right? If punish forever, then we can't do things, right? No matter what had been done
T period be gone, then let bygone be bygone. Okay, so we have been T period, okay, have been punished for T period already, right? We have been in fights for T period, okay, and then regardless is whatever, then we will resume. Okay. Now, when we will be punished, the punishment is last period, okay, is we did not get any, I did not get any profit, okay, and the God said you are cheating, okay, then I will start punishment, okay, and if we have been the punishment, we continue punishment, okay, because we have to, if we punish, we have to punish for T period, right, big T period, okay, so as long as it is still not done the punishment yet, we will do the punishment. So basically the following, okay, so look at my profit, okay, if my profit is 1, of course I continue, okay, if I look at my profit suddenly becomes 0, I check the God tell me continue, and I continue, okay, if the God said no way, this guy is cheating, then I start punishment, and I punish for T period, okay, if of course then I would, after T period, I will go back. Is that clear what is doing, right? Remember, my strategy depends on the profit, right? And also what happened to God said, okay? Remember, this tempo is observable, so everyone knows whether I engage in this the God thing, okay? That's a coordination thing. So look at this little bit slightly crazy stuff, okay? So remember that you have good times is 1 minus alpha probability, right? The notation is good state, okay? So this is the good state, right? If it's bad, you get 0. So good, this is first, this is this period outcome, right? If you collaborate, right? It's a good time, right? You set the price 1, a good time, then you earn this profit 1 with probability 1 minus alpha. With probability alpha, you get 0, so we don't have that. It's just alpha times 0. That's the profit for this period, okay? And if you continue next period, okay, if you continue collude, right, according to equilibrium, continue collude. If this is a good time, you also get 1 minus alpha. Right? And but if the bad time, okay, it depends on the God set, right? If the God set continue to continue, okay, and you continue means that you continue in the same continuation payoff, which is continue the same game, but a discount. It's just a recursive, right? Because the game continue as this one, right? And you discount it back, right? And but in the bad time, then remember we will punish ourselves for T period, okay? So after T period, we'll go back to normal. We go back again, right? During this P period, everyone gets 0. Okay? Is that okay? Is that okay? So let me repeat it, right? This period, you get this payoff, right? It's a good time, okay? If it's a good time, next period, what happens next period? Under this probability, you get good time. If bad time, then you will continue the God forgive him, right? But if bad time, then you wait for T period to resume because T period gets 0. Is that clear? Maybe I draw a diagram, right? Because like this, right? So nature decide whether it's a good and bad, right? This is good, This is bad. Okay. And if good time, then you get this payoff. Right? And then next period, what happened? You do this again, right? You destroy again, right? This is 0, right? Because you get that time, you always got 0. So you get 1. So the payoff in this period 1 is like this. Afterward, next period, do the same, right? If good time, then what happened? You continue, goes on is 1 minus alpha, you continue good, right? And if bad, right? Remember the bad time. Bad time, what are you going to do? Roll the dice, right? The dice will say if beta said it's fine, 1 minus beta said it's fine, then continue, right? So that's 1 minus beta, you will continue in the good time, right? Right? Otherwise, beta, you go to punishment. You go to the punishment in T time, right? So T times afterward, after T time, then you go back to this one. Okay, maybe I don't draw this guy, maybe less confusing. So that's so something like that, right? So this is starting point of the initial, right? The cooperation point, either good or bad. If good, then you continue to go, you maybe join this way, right? Maybe this is easier. If good, then you go back to here, right? If bad, you also go back to here with probability 1 minus beta, right? And if bad thing happen, right? Then you get 0 for T period, right? 0, 0, 0 for T period and go back. So that is high. You have 1 minus alpha there, 1 minus, you have alpha times 1 beta, you get back to here, right? And if you get bad, then you got the bad luck, you get stuck for T period, then you go back. So that's how you get this. Is that okay? Is that okay for this? So the first one is you get the immediate payoff for this period. You get 0 for nothing, right? But next period, what you get is if they're good, then you continue to be good, right? Depends on the good luck, right? But if this is bad, then you depends on it depends on where you are. Okay, maybe I should draw a picture in the slide. Maybe I should draw this picture on the slide later. Make sure that you understand what's going on. Okay. And you can rewrite this is going to be rewrite this, right? Because this is no deviation. When deviate, what you're going to do? When deviate, you only get deviate, right? You grab the whole market, all right? Your whole market. In the good time, the bad time, you get 0 anyway, right? Because the whole market is just 2. You grab the whole market, a good probability. And then you will be looking at the same, right? Even though you do bad thing, the God will forget about you, right? If you get lucky, because you're cheating, actually go to here as well, right? You don't know the cheating or bad, right? You go to here. You may get forgiven. You're not forgiven, you will get punishment for T period. Why this one? Oh, because when now you deviate, you be a bad guy, right? You bad guy, then you get $2 to the total market. In the good time, bad time, you get 0 anyway, right? And then, but if you are because you are cheating, so the other guy must get 0, right? The guy for sure, the other guy gets 0. So the other guy gets 0, then the other guy will say, okay, look at the tempo. The tempo said
the number is better than this, then he got forgiven, right? Although I'm cheat, then I forget, right? I cheat, the other guy forget me. They will continue to be a good outcome, right? But if not, the God doesn't forgive me, then we enter into T period of nothing, right? Because the punishment is like this, right? Because the God, you look at temple, decide whether we will punish me. Which one? This. So delta raised to the T plus 1 period, because you get T period of 0, and then afterward go back to collaboration. So the rule is like this. Okay, look at this again, because you understand it will be, if collaborate, continue. Collaborate, continue. If not collaborate, look at this x. If x is bigger than beta, big number, you forget him, right? If we punish for T period, then we continue to collaborate. But if I have 0 profit, the number is small enough, then I will punish for T period. T period of 0. Okay, I will set price to 0. So that means that, look at this one, when I deviate, okay, I will grab the whole market for sure, right? Because I charge the price like slightly below 1, right? 2 minus 1 minus epsilon, right? But this is the whole thing you grab, right? And of course, if the bad time, there's no difference, right? But the other guy for sure will have 0 profit no matter what. So he will ask the God, right? Look at the temple, and if I'm lucky, I escape, right? I escape because the number is bigger than beta. I escape, right? Then we continue. We forget, right? Because I'm lucky. I escape. I cheat, but I escape. But if I can't escape, then I will got punished for T period. Everyone gets 0, and then I resume again, right? Because that's the idea, right? Is that okay? So please ask, because this is a little bit slightly more complicated than the other part. Okay. So this is the requirement. You of course put that number in, right? And then you can check. All right. Of course, you combine this thing here, right? Right. You can combine these two conditions. You will figure this out, right? Because you put this one to the left hand side, right? You can solve this. Solve this out. Okay. And you can check. Okay. If and only if, okay, this thing would happen. Okay. And basically this comes from here, right? You just put this on the left hand side, or this on the right hand side, right? Just put this guy to the left hand side, right? Put it here. Okay. And you can see if alpha is small, then it's okay, right? Because alpha means what? Alpha means bad time, right? So if there's not too much bad time, then we can collude, right? You can imagine if alpha is super big, then no matter what you do, you always get 0, then I cannot sustain punishment, right? Only if happen that the thing we can't control is not that high probability, you can do it, right? And right, it depends on patient as well. So this is the idea, right? So the idea is this is the proof behind, but I think it's easy to see that, right? You can just take the infinity bear to 1, and then everything would works as well. I'm not going to prove it, but this is the idea. Okay, this is if you want, you can check the JET paper. But that would be very similar. Okay, and is that okay? Not going to show you the more detail. That would be fine. Okay. Any question before we proceed? So I mean, the last one is very complicated. Okay, I don't expect you know how to solve this or the price collusion. I'm not expect you to solve it. Okay, but at least you know the Fock theorem, right? The standard thing, right? So I think it's if you worry, all I can say is I think you can take the version up to 62 onward. You can will be technical consider. So you take revision up to 61 will be fine. Okay, but I do recommend you. I mean, if you want to work out the repeated game literature, that was something that will be beginning, right? You look at the repeated game textbook. This is the starting point. These two games. They will all look at this game and the variation of that, and that will try to answer the question, right? Because a lot of business relationship are repeated game, right? And its problem is always the imperfect monitoring, right? And of course, the literature actually go to what we said the private signal that become much more complicated, right? Because here is I have a sunspot, right, which everyone observe, right? But what happens if I can't really observe the signal is for my own observation, okay? But they may be correlated. Can it be anything, right? Can you still sustain collaboration? Okay, there are many things that in the literature to generalize this idea. Okay. Okay, and this may make sense why firm in the real world actually use some randomizing strategy. Just look at the moon, look at something random to decide whether they collaborate, or in history, right? We see whether we continue is determined by some cracking of the tortoise bone, right? B.B.A, right? These are all other things, whether they decide, right? Whether this is the idea. Okay. Now, before go to break, let me quickly review the next topic. Quickly, 1 or 2 minutes. Time to talk about this. Okay. So here, there's a lot of things to cover. I think I cover half of it. I can. So this topic, you can see we have pretty ambitious, right? So we tell you that how we play the game when player don't have complete information, right? Because so far we say that everyone have perfect information, right? And it's the game set up, right? And you know what other guy can do, what the payoff are, right? But in reality, there are many situations where you don't have good idea what's going on for the other guy, right? You may not know whether the other guy has, say, high cost producer or low cost producer, whether they're efficient or not, right? There's a lot of uncertain. The question is how you will be able to make decision there. Okay. And the question is, if you don't know, then there's no way to do anything. Okay. So that means that to solve this problem, we have to give some structure, right? If you don't know how to make decision. So that is the Hassiani's idea. Instead of incomplete information, we call imperfect information. We don't know, just like the standard idea probability, right? We don't know, we cannot assign probability. But we can assume we know what is the state of the world. We know the sample space. What is possible? If we assign probability to what effect may be possible, in that case, we can talk about Nash equilibrium. And the nature we decide, as a nature is doing random strategy, right? Nature decide which tree we're looking at, right? The idea is, okay, I don't know, suppose a game where you have player 1 has no income information, player 2, right? You can imagine that actually player 2 can be high cost or low cost. And it's a nature, which is
hidden player who doing randomizing strategy, right? He was randomized maybe probably 1/2 and 1/2, right? And say firm 2 is a high cost type or low cost type, okay? And then he can decide how much to produce, right? And firm 1 have to decide, okay, what to do, right? Maybe produce high or low, right? High or low, okay? But the problem is firm 1 doesn't know where he is. Right? You can represent this, the base end game in this way, right? He doesn't know actually where he is, right? But player 2 know where he is, okay? Player 2 know whether he's high cost or low cost. That is given by nature. We can solve this game, okay? And the game of this, we will later see this called Bayesian game. And if you solve equilibrium in this, it's called the Bayes-Nash equilibrium, the standard. Same. You just change the game into something like this, okay? And then we can solve the model, okay? But we will talk about this after. And you ask, okay, why we care about this? This is very important application, as you can see from the slides. The topic is called auction, right? And auction is you have an object, you don't know how much to sell, because the how much to sell depend on buyers, right? You have to say you want to set the price and let the bidders or the buyers name the price, right? And each buyer doesn't know the other guys willingness to pay, right? They make the bid, right? So that is a standard idea, right? Maybe I know how much to pay, everyone knows it, but I don't know yours, right? In that case, that would be the idea, right? So that would be something that we'll be working on after the break, and probably we'll at least cover the first 2. Auction will be we'll cover 2 weeks later, because I said next week we'll have a we don't have class, but we'll make sure that we cover everything, and then if not, we'll do the makeup. Okay. So let's a break of 15 minutes. Feel free to enjoy the candy if you want to. So let's resume at 14:32. 33. Okay. In case you have to go. Please take some candy. If you want to. 因为我下周去了北京，有不用开会，所以我就大脑没办法想。我再看看怎么补一下，我补一下，肯定会跟这次都。再2分钟。哦。哦。不在，很怕我来的时候飞机我在机场就上了。我刚去年有参加会议，我出了飞机之后就没来上课，不好，还是把它地票不安全。那我的内容这个 bug 我可能能教得完，但是我会找，这是我在考的是一个在教你，或者像大家来不来的出来，没有人讲，我教一遍把它考。这个考试我们要换钱了，啊对不对？就没有额外的。应该不用了吧？除非我觉得如果你们不想补课的话，我就给你们提供这个。这个也行。最后一节课，如果以后看看你们要不要补课，如果你们不想补课的话，我就把这个相关的东西用。我到时候我猜一些问题，问你们这个情况，如果你们不想补课，我就把相关的东西你们就听说用最后一节课还是大家。到时候问你们了，我到时候再给英语查一下，没有干懂，完全没问题。
这个东西，它的主要的 implication 是在于，就是在他给的这样一个特定里面，就是存在这样一个 strategy equilibrium， 它主要说的正确的问的问题这东西，所以要把像这个如果想让它擦成绩的话，就必须要让QH 要低一点，这些情况 OK， 所以它重点不是在于， 就是它重点不是在于证明这个图层的那个原始，
对
它的
在证明这个栏高有一点，重点在栏高平均开始做的事情，
OK，
对吧？就是这个价格是不一定。
就是这个delta bar 什么的设定里面就它的原本的那个模型设计里就有，对它设计
对，待会儿就设计的原因。
所以它现在是，所以它现在就是，就它设计了它假设了一个就是有，它设计了一个 market 一个 world 在一个系统上，在这个系统里就是在这个系统里面，如果这个 player 拿 discount 如果 discount 大的话，如果 discount 大的话，就会是1，如果 discount 小的话就会是0，然后同时还有 good state 和 bad state
有中间的，比如说liquid 的 discount 出现好的情况的价格很差的情况，
好的情况下，就是这个好的情况价格比差的情况低，这个是它
就是最重要的中间。
最重要的贡献。所以这个是
因为一般来说，你觉得好的时间的价格高，
对，
害怕就不是。
我觉得好的时候价格会低。
对啊，这个就是看它cynical口在宏观里面我们说的，有什么 good time 的 price。
所以这边的话，它是只有一个公式，但是并没有证明，就是它框架里面这样。
那这个是一嘛，这肯定是price 分大于1，price 分大于1嘛。所以这个框架是这么一个，你说这个 PQL 是大于1，因为这个是手艺。
所以它他提了一个这样一个框架出来，就这样一个就是在 good state 的在 high 的情况下，商家会去定价的这样一个 word 出来，然后他就证明这个 word 是可以自圆其说的。
对。
如果他这个没有办法通过，如果他这个东西没有办法通过调 P 来让这个 finding hold 的话。那他这个他就相当于是 reject 了他提出的这个这个 word 对 existed OK 是这个意思。
对，证明传在这个东西。
OK， 所以就类似于
它不是我一个理论，它就传在这个经验教育。
对，就类似一个 hypothesis test 的感觉。
这是个 story 了。
OK， 就是我先整一个 story， 然后这个 story 里面有这么一个
句嘛，
对，一个 equilibrium exist， 然后然后我再把它不等式列出来，然后我说，然后看它有没有冲突的地方。如果它 hold 的话，那就说明我的这个东西没有被 reject 掉，至少它存在过一个，虽然有别的也存在，但我这个存在。
对，
就是它如果被 reject 掉了，对。
估计有点挑战了。对，有这个看能力的，就给他看有一点。对这个太有点，我说有点因为有一点水平东西，就刚开始东西其他东西，这些水平的水平东西，其他以前那个东西都麻烦，刚才来的就是那个 A R 那种，刚才那个东西必须是明白的。每堂课的点没把它弄到啥呀？我每天都讲这个，肯定不行嘛，就是讲这个一种，你们肯定方面。我们经济为什么我考得上？哎，有些错了，你不能再打，人们不开心过关。而且我们也不行，反正水东西有用，我就叫有什么东西有用，跟你们做的真的是东西比较重要。PhD 啊，大家都会要看书的大书的，大家技能很不缺。什么重点告诉你们，那个在看书，就是我们总大部慢慢讲。对，那很多东西对吧？对吧？
在地产，啊，这是最好的最好的，在这个香港地产，股票的但是你讲的肯定需要看的理不要人去做一百，我要来考试。我天天都没有这。对，还是我好的。我的话，我现在有地方有一个来是花了大一下面现在的有几特别是的下面下面的大号的，对这些孩子，对这些孩子，会有很多的厉害，大就可以有点企业的蛋糕。因为现在地面上的大码有点多大，欧洲的话，那个北和大码就大码就这个可以减小对它的对那个州密度来这个是吧？谁看这个谁放的？基本上，很多人是不是现在有很多人学，可能有些。我到时候差多问你，再差多问你，互相补充的，可能这个周末上面，大概到大会内，大概当然有些偏过超难一超难一点，要玩一大个来吧。如果在线上跑，这城市就是我在学校做的，就会查过这些，查 GPT，还有一个他在录，原来那个网络隐私的查，记得我让大家稍微花一点精力去做才有。对，反正就是你拿的，你能够。爱的对吧？这样子好像情况一般，爱在哪里？好，也了解一下， 对，但是你可以大概看到，对，很多东西有什么 CO 的反应，不记得吗？应该。或者还有都结合了，我也大多也是不知道，不能当然是，我也是有大半去，也是这次。
这个重点不是不一样的东西，这个重点不是分析，
对，是，但是我也有，没有吧？大概就是看得出来有点是，大概有些但是我在还是有些不能改的，只用不改的就把它把下来给选了，有点手上有写，会把。但是它这个大家都属于一个我是有一样，等于方法不也是差不多。一样。一个嘛。没有什么很大的事情，还是这个。
So I hope you enjoy the break and also some tricks that I offer you. Okay, don't put trick on me if you get a treat. So let's finish it because we don't want to keep you for too long, right? I don't want to overtime. So as I said, instead of we don't know, you just don't know which. That's the idea. Okay, that is the idea. Okay, so that is the main changes. Of course, whether this applies or not is another issue, but there's a way to solve this problem of we don't know. Okay, we assign probability to what might be there. Okay, so and how do you embody the idea that I know more than the other player? It's called a type. Okay, I know my type, you don't know my type. Okay, and in particular type is, let's say I have high cost or low cost, is my own type. Only I observe my own type, you observe your own type, okay? But I have probability distribution over your types. Okay? You may be high cost, low cost. This is your private information, okay? And I may be high cost, low cost as well, but only I know it, okay? And you also assign probability over me, okay, as well. And the probability here is the belief, okay? And of course, why you call belief is the Bayesian idea. Why? Because you cannot use classical ideal probability, right? Classical ideal probability is whether something hasn't happened, you cannot call probability, right? Once thing happen, you cannot call probability. That's a classical idea, right? Because just like roll a die, right? Before you toss a coin, roll a die, you can say probability. But once you roll it, you cannot say probability, right? If I toss a coin, I cover it, okay? There's no more probability. Either it's head or tail. But you can still say I have half of the belief that is a head, half of belief that is a tail, right? So that is called the Bayesian. That's why I call it Bayesian game. The belief, the Bayesian comes from. Okay. So the most common assumption that we need to assume before we proceed is we call common prior, common belief, and which is something that we assume in almost most of the model we apply. I mean, there's of course a paper that try to dispense of it. But what is common belief means that we start with a probability distribution that's by the nature, right? The nature decide what can be the possible type of U and I that's come from the small p. Okay. And this is the distribution of T. Okay. And the Bayesian means that given my type, nature tell me my type, okay? And what is all your type, okay? Depend on this conditional probability, right? That is the Bayesian game idea. Let me repeat the statement. At the beginning, nature will tell us how likely that I'm type 1, you're type 2, and how likely that you are type 2, I'm type 1, so on and so forth, right? They're all possible combinations of types. It is given, we know very well. Common knowledge, everyone knows, okay? How the nature being decide, okay? And the nature will draw something, I know my own type, okay? And what is my belief on the others would follow this conditional probability. This is the idea of what we call common prior. Of course, this is very technical, and we always assume in the background this is true, right? The same as when we talk about Nash equilibrium, when we solve that, we assume there's common knowledge of the game, right? We know the game, how it's being played, what the payoff, everything is well known. There's no uncertainty, everything is well understood, okay? That's well understood, this one. Now we start the game. The game, not surprising, not complicated, okay? The game can be described by 5 elements. The first one is well known, N is who are the players, okay? The second S is also well known, what is the strategy, right? That's complication here, but the strategy, what can you do, okay? But it will be a little bit complicated, and what can you do, okay? The thing is, there's a type set, remember, what can be the type, okay? And this belief is given your type, what you think about the others, okay? And the strategy, that's the most complicated thing, is depending on type, what are the action? Why the case? Remember the tree we draw, okay? Suppose only pair 2 at types, right? The nature, okay, may decide P or 1 minus P. Player 2 is a high cost type, right? Player 2 may be low cost, right? And then player 2 decide maybe he produce a lot, right? High or low, right? Q high or Q low, Q high or Q low, okay? Okay. And player 1 doesn't know, okay? right? In that case, player one only choose one thing because he has only one type. He has no public information. Okay, and player two would have two possible type, high or low, depend on nature draw. Okay, and depends on the nature draw, he have to say under high what do you do, under low what do you do, because this is a two sub game, but not two scenario. He can distinguish, which means that depend on type, he have to tell the thing. That's why it's type to action. Depend on the type. It's high, what to do, low, what to do. Okay, so do remember yourself here is you have to specify the player what to do for all possible types. He gets chosen. Okay, so that means the payoff will be like this function. Okay, it's a little bit technical, but you will see very soon what are we doing here. So this is the base Nash equilibrium, which is not surprising. It's simple. We assume the player are expected utility maximizer, as we have assumed. So what is equilibrium strategy? Would be that player I is choosing an action, and given all the other players choosing this, what is payoff through the expectation, right? Because you have to think that if the other guys are high, this is my payoff. If the other guy is low, this is my payoff. How likely is high or low? I look at the expected utility. Okay, so that is what is going to do is I know my type, I don't know your type. Your type is high with half, low is half. So what I'm going to do is I choose a strategy. I have half the time I face high type of U, one half low type of U. So I would say, okay, what is my payoff on expectation, right? Expected utility. Okay, looks tediously complicated, right? But don't worry. Let's go to the example because we never use this definition anyway. Look at the example, it will be very simple. This has looked crazy. Let's look at this game. You look at this game, everything will be very simple. So I will go very slowly on this game. Make sure you know how to do it. Okay. So this game is not complicated. So you have marginal cost C, and player two have marginal cost two type, high or low. Okay. Two type. And the nature said your high reported theta, low minus theta. Okay, the only two choice. Okay. And player one, this belief is common knowledge. Okay, because that is common prior assumption. Now look at firm two. Firm two has to design under high type or low type. So that means that he have to separate two scenario. If high type, okay, he's going to face this problem. If low type, he face this problem. Fictional. Okay. And of course, if high type, he'll produce high cost, he'll produce less than the low type, right? Given whatever Q1 is. Okay, to solve the model, find the FOC, that shouldn't be difficult. You know how to solve that one. Is that okay? This is okay, right? If you want, I can solve it for you, but just standard FOC can solve it. Now, this is nothing new because there's like the two possible case, right? The only troublesome part is firm one. Okay. Firm one is looking at the expected profit. Okay. At theta, he's facing high type. At 1 minus theta, he's facing low type, right? Here, this is the high type opponent, right? CH. And this is the thing that he faced a low type. Okay. But remember, firm one cannot choose. He didn't know with high to low type. He only can choose one number, right? Which is Q1. So you have to balance two opponent, right? Right. So he's somewhere in the middle. Okay. So as you choose the Q1 that it would maximize his payoff, right? Just the differentiation. Right. And you solve this out because turn out to be this linearity. That's a very nice result. Is the response, best response, okay,
will be probably good time. You think about this, bad time with this, right? This A minus C minus Q over 2, right? So basically it's the average response from the good time and the bad time. Sorry, good high cost opponent, low cost opponent. So if, right, because if theta equal to 1, right, this is what he should behave when he's facing high type. If theta equal to 0, this would be the outcome that he faces low type. Okay, turn out to be the optimum response is a expected response. Okay, of course this is very special. Okay, this only holds true for this particular example. In general, this is wrong. Okay, in general, this is not the average. It's not the average response in the comparison game. Okay, turn out this one is the case, but in general, this is wrong. Okay, in general, this basically doesn't hold. Now, once you have this with best response for player 1 and player 2, right? Base Nash equilibrium means that I have best response for everyone, right? So it's a fixed point idea. So basically, I solve 3 equations with 3 unknown, right? Player 1 have only 1 equation, player 2 have 2, right? So I have 3 equations, actually 3 linear equations with 3 unknown. So it can be solved, right? And it's independent, so you can actually solve it, right? So it's put this thing into Q, right? Put it there, right? Then basically put this number and this number into that first, right? Put this second and the third in the first one, okay? Put it there, okay? Collect terms, you get this guy, okay? So this is how Fermat would do. Is that okay? I just wait for 1 minute to see if you are seeing what's going on here. And this will be important because this is the illustrated example. I don't want to go too fast. Let me know if you have any question. Is that okay? Because this is very useful, right? Because very often we don't know how good your opponents are, right? And if everything's linear, model is rather simple. Okay, that's a very nice outcome you want to use. Okay. Now, once you know how firm 1 responds, then you can put back into firm 2, then that end up in here, right? There's a plug in, then solve it. Not going to do step by step, but you can see that we have 2 outcomes here. Okay. Now, of course, this is still a little bit tedious. Okay, Mathematica or whatever software can solve quickly. So here is the outcome. But let's see what happened. Look at this question. Now, this is a little bit messy graph. So let's try to make sense out of it. Okay. If you remember how we draw this blue dashed line, it's the standard thing when we have complete formation. Right? The blue one is standard. It's A minus C A minus over 2, right? This is the same. There's nothing new from that one. Nothing the same thing. Okay, the blue one. And this is best response, right? For low type and high type. Okay. And if I know the consumer is high type, this is the one, right? Confirmation setup. This the red one is the complete information result, right? So if you are high type, for sure, green would be the Nash equilibrium, right? If I know
the guy is for Swallow type, blue is the equilibrium. Okay. And what is our result saying that we have theta high type, one theta low type? Actually, it's the middle by ratio by theta. If theta is half, then it's midpoint of these two. Okay. So of course, this is the artifact of this linear response. Okay. In general, it's not like this. In general, can be somewhere here, can be somewhere there. Need not be on the line. Okay. Can be anything. Okay. In general, because later you will see. But in this particular case, turn out to be very nicely, right? Your response is on average of this response, right? On average optimal, right? So if half of time is good, half of is bad, then your response will be halfway. Okay. Is that okay? So don't worry. I think you will be solving this kind of problem in your assignment if I later give you. So you solve it, then you know how to do it. Is that okay? Don't worry. Again, you have to work on it. There's no shortcut to knowing without ever working a problem on that. Now, auction. Try to see if auction is something interesting. Okay, because auction, I think, for those who do finance, or real estate, or who environment, they do auction, right? Environment, they all the quotas and the green gas, the carbon tax, many things they do auction, right? The environmental thing, the stuff is auction, and the question is auction. Why with auction, right? The problem is if something that is so common, you should use market, right? We just sell in the market, the price is clear, no one is having information, right? Just like apple, orange, rice, you don't need auction, right? Because it's common, homogeneous. But the problem is I don't know what to sell, right? Because I don't know how much people want to pay for it. Like antique, right? Something is rare item. I don't really know how much people want to pay for it. It's not commonly occur. So it's not clear what to do. Like the seafood, right? In Japan, right? There's a very famous, right? Famous seafood. Probably now we have something similar in Hong Kong as well later, right? The seafood auction market. Why? Why you have auction? If you remember, you go to Japan, right? There's a famous place they sell, they auction the fish. Why? 竹地市场那个 fish auction. So you can see this type of auction, tuna auction. Okay, there's got a very big fish, and they put the price on that. Let's see if I can play something there. So something.
Alexa 傳承母語保護，匯聚三大核心元語成分。
今日も初競りということで大変注目されているところでございますが、今年大いにこのドイツ市場盛り上がって、その象徴となることを大変期待をするところでございます。
So you can see the doing auction.
And you ask why they do auction, right? Why don't they just sell the price and post it there and then that's that?
おはようございます。大水局
The reason is being that you can notice these fish are big, right? It's not some regular fish, right? And only the high-end fish are doing this way. The low end they don't, right? And why they do it in this way? Because you don't know how much people want to pay for it, right? Who want to pay for this expensive fish? A high-end restaurant, right? And high-end restaurant, you don't know how much people want to pay for it because people can pay for a lot if the quality is good. And the quality varies, right? It's not from a factory. They got a tuna from the sea, and it can be very big, can be very small, right? That's why you can see a lot of people are trying to look at it, right? If you look at the picture there, is they kind of cut the. You don't know the quality. You have to check the quality, right? So that's why you can see this. I remove it. They cut the tail, and so where did I? Let's see if I still have the picture with me. Do I? So if you still remember this one, right? There, I don't know if you can see. They cut the tail, and you can see the meat inside. And that guy trying to look around. Everyone trying to look around how good is the fish, and then you can see this guy, right? This guy. You try to hit the thing and try to see how good they are responding, and check everything. Okay, so and everyone have different value over this fish, right? Because depend on the restaurant you are in, and then the reason is I don't know set the price, right? If I know, then it's done. So then the way is the seller want to is unique, right? There's a variating every day is different. The fish depend on where they got the fish, whether they're lucky, right? And also the supply is different every day, right? If we have good time, but my opponent have bad time, right? It depends on how good you can sew. It depends on what they did today, right? What are other restaurant are bidding, and so on and so forth, right? Because you will not every day in a big fish, right? So it depends on how customer arriving. And that's why one alternative to the market is auction, right? When you don't have the market there, right? There's no market, then we have the auction, right? So that's why in this literature, we call the market design, right? Because you don't have market, you have to design the market. Auction is one way to, in the literature of economics, it's called auction. And the special about this is there will be a price formation like the market, right? Remember how market works is people set the price up and down to satisfy demand and supply, right? But auction is rather explicit, right? It just, we set the price is determined by the rule such that the demand equal to supply, okay? And this is different from two things, which if we have time, we can talk about. We'll talk about the fixed price sales in supermarket, right? No matter the demand supply, right? The price is there, you can come buy it at any quantity at the same price. Right? Another one, if you have time, we talk about this is bargaining. I think we have time in the makeup class, or once we finish everything, we have time, we talk about bargaining. Okay. And bargaining is, as I said, right, is the price proposed and counter offer and offer between two parties. Okay. And that can be modeled by subgame perfect equilibrium or corporate game. So we'll talk about those. So the word auction actually derived from the Greek letter means increase. It's augment, right? Means I increase, I add, because the price starts from the very low. So one of the earliest, one of the most also interesting history about auction is woman, actually marriable woman, actually ran auction in the public square. Okay, and the price actually, remember, it's not the standard auction, it's a Dutch auction. You start from a very high price, okay, and if you want to marry this woman, you pay it, then you get the woman, okay. And of course, if no one gets it, the price goes down, right? Keep go down, and go down 0, negative. Negative means that the father pay you to get her out because they cost a lot of money to keep a daughter, right? At the old days because this society, right? People die every day, right? Very easy, right? Because it's old day, they fight and thing, and it's not easy to survive, right? Then the food is not that easy, right? Because these days, right, men are killing each other, right? So well, that's why there's a lot of women being auctioned, because someday the man will die, then they will get auctioned again. Anyway, another famous auction is in the Roman Empire. So the Roman emperor, the emperor actually got killed by his guard. Okay, and the guard, of course, probably cannot become the emperor, right? So because they're not smart enough anyway, because they just know how to kill. So what they do is they try to say auction the throne to people. Whoever promised to give them most money would get the throne. Of course, the story goes on saying that the guy who win actually promised too much, and he can't pay. He killed by this guard again. Okay, and of course, people end this series saying kill all the guard, but that's history. You can look at that. It's very funny. I mean, because it's very funny, right? Because try to sell something. That's what they call the winner's curse, right? You win, actually lose, right? The winner's curse is you win, but you pay too much, then actually you're losing, right? But anyway, that would be something funny. So as I already said, the fish in Japan, that is one of the very famous. All the time you go to tourists in Tokyo, you go there, right? You go to the place with the morning, you go to see the auction. And the other one is one of the oldest auctions, it's called the Dutch auction. It's the Netherlands, the flower. They start with a high price. There's a clock, keep going down, the price go down, and they say yes, then the flower belong to you. Okay, very similar to the Babylon woman marriage auction, right? But this is for flower. So the bonds in the US market also sold by auction. And there's a COE, which is the car ownership. Certificate of entitlement is like you own a car in Japan, sorry, in Singapore, or I think in Beijing or Shanghai, I don't know. They also do the auction as well. And this is one of the biggest thing actually 10 years ago when you have 3G network. And actually one of the people who say economists are really useful is because economists design the way how to sell the spectrum, right? Which bandwidth for the 3G and 4G, they sold that. And that generate multi-billion-dollar for government. And that is the reason why people said, even though most of the econ research are useless, do not generate monetary value, we can justify by saying that we design very nice auction mechanism that allow government to get a lot of money. Okay, so this is what they said. I mean, agree or not, but that is what people claim for that. And IPO and eBay, right? People already know IPO is a public offering, and eBay, probably I hope you know already, is by auction. And now we talk about standard auction. Usually we see 4 different types of auction, okay? And literally they're very similar, okay? And the result will be very similar as well. But in the literature, you will see that one is better than the other in some sense, okay? The first one is English auction. This is the currently most commonly done in the public auction. So basically everyone's in the room, okay? And the price basically keep going up. We will just call the price, right? They start at $10 and you raise your hand, they'll go up by say $10, so on and so forth, right? And until there's no one left over, then you'll be sold at that price, right? So this is the ascending auction. The price goes up until there's no one. Basically, just like everyone raise your hand, okay? The price will go up. And if you don't like the object, then you put down your hand, right? Until the last hand is there, then you pay the price. Okay. And the other one is Dutch auction, we said, right? It starts with a very high price. Okay. Whenever someone raises a hand, then the price is being there. Okay, the Dutch auction. And these two other one is also commonly used in the world is when that the Dutch auction and also the English auction. Okay, it's the thing that everyone have to be in the same room to do this, the Dutch auction house or what, right? But sometimes you really don't want people to do synchronous auction, right? People come and see the object and write down the price, put in the envelope and put there, okay? And once everyone want to buy, put envelope, the guy open the envelope, okay? And the one who win to pay most would win, right? This, we can do it off. That's why the online auction is like this, right? This is something that can be done in this way, right? Or this is another one because second price auction, which means that still the guy who want to pay the most win, but you don't pay the price to name. You want to pay, you pay the price only the second highest, not your price, but the next highest price. So it's very tempting, as I learned the first time, is why you do this, right? Why don't do that one, right? This make more sense, right? You pay high, you would charge, you earn more money, right? Because you pay the own price rather than pay the other one. Turn out that no difference. Okay, in many scenarios, actually the revenue for the seller has no different expectation. Okay, and later we'll talk about. Actually, this is more preferred. The reason is we'll call what we call surge proof. You will tell the truth. Okay, there are no, for this one, it's just a weakly dominant strategy to tell the truth. You need to guess. You actually don't care about what others think. You just tell what you think. Then you're done. We will try to prove that. Okay. But this one, you have to guess, right? To form the idea, okay, what other people want to pay, right? I have to try to beat, right? Because I don't win, I want to beat you guys, right? But I don't know how are you going to pay. I mean, I have some idea what you guys want to pay, then I want to beat it. But I don't want to set my price as how I want to pay, because otherwise I left with no surplus. So I have to balance the idea that I have some surplus if I win, but I also want to balance I'm more likely to win, right? That's a trade-off, right? If I have a higher price, then I'm more likely to win. But I have less surplus. So there's a trade-off, right? So there's the optimal price there. There will be some strategic element there. Okay. But this one turned out to be there no strategic element. Okay. Because you're not paying your own price. So you don't need to worry about it. Okay. So that's why this one will be more preferred. Later you will see in many cases you will prefer this one. But of course, there's some cases you will prefer the first one. But this is not the thing we cover. So the first thing I want to say is the simultaneous auction in the same room or asynchronous auction, and that's equivalent. Okay, turn out to be the ascending auction, the English auction. Okay, in the same room, the price goes up until one sun drop out. Is the same as first price auction. The idea is that if you decide in English auction when to drop out, it's same as this is the price you submit. Because we say no, actually it's the price that you would try to do that. This same thing. Okay, if you behave in this way, okay, and will be same as the Dutch auction. So because the price goes down, you say yes. Same as you keep when the price you get out. Okay, the same thing. And the second price auction and this open as an auction the same, right? English auction, right? If the price beyond what you want to pay, then you just get out, right? So that's why English auction is very common, right? Because whether you stay in the auction, is the price is still below your value, right? You still remain there, right?
If you're beyond, then you should just get out. Right? Then same as the second price CFP auction, because you just tell them the truth, because you are not paying more than what you're supposed to claim, so you always have some surplus, right? And turn out to be the price only determine whether you win or not, right? The surplus depend on others, right? So you tell the truth actually have no harm, right? Because when you win, it only depend on whether you win, right? How much you gain is depend on others. But you win, you must have surplus. So there's no trade-off between that, right? Because you don't want to claim higher price because when you win, then you may win at a lose, right? So that's turned out to be these two things, okay? And let me quickly define the game, okay? And in this model, the player can be the buyers and the seller, okay? But of course, the seller is a design problem, so the seller is not a player in this game. It's a one step ahead, so he decide what auction to do, okay? But once he do, he can commit this is the auction, okay? And so the only thing is the bidder, okay? And the bidder decide how much to bid, the auctioneer design the format, okay? That's why they call market design problem. Design what kind of stuff. And the payoff, of course, depends on the rule of the game, right? Whether second price auction, the first price auction, or many other, maybe can be third price auction, any type of auction, okay? And because the auctioneer, right, doesn't know who he is, then usually there will be a surplus between the buyer and the seller, okay? Everyone will be having some happiness. And you look at the literature, you will see there are at least three types of auction, okay? In our class, we can only do one, private types, which means that every one valuation to that will be drawn from a IID distribution, right? You draw your value, I draw my value, is independent. So if I like it, doesn't mean I can't tell you whether you like it or not. That's the most simplest model, okay? The other one that is more common in natural resources, so common value, right? Because how much the value to you is just you sell the oil to others, right? That's common value, right? There's a resale value, things this is a more common value, right? Everyone the same valuation, right? The oil pit, the oil drill, the oil land is just to sell the oil, right? That's the thing you care, right? And this one, the last one is the most common one, the most general one. It's called interdependent value, right? Is I like it. If I make a high value, likely you also make the high value, right? But maybe I can use it better than you. Maybe say, for example, we are trying to buy land, right? Develop this land, right? I'm a big developer, or I have land nearby. I can connect them together. This land to me have higher value than you, right? But if I value high, you also value high as well. But maybe I'm higher than you. So there's some relationship between the value, okay? But this one probably is IID, okay? I high doesn't mean that you high, but interdependent usually means I high, usually you also high, okay? Is that okay? There's some maybe you can say there's some correlation between the types, right? You can use the same idea. So let me finish this slide. Okay, I talk about the problem then quickly and then, okay, I will just 1 or 2, give me 2 minutes, okay? So here is the simplest problem is this auctioneer has a object to sell, okay? In general, we assume that this has a 0% value, that the auctioneer don't need it, normalize to 0. And if sold at the price P, the payoff is P, it's not sold at 0. And there will be M players, and each player have valuation VI. This VI is private information drawn from some distribution, okay? And the payoff will be cosine linear. You take the value minus the price, you pay the P, otherwise you got 0. Okay, so this is very standard model, okay? And here's a question, I'll end with this slide. So the question is, can we always give the object who value the most? Because the efficiency, right? If you get it to, because the price cancel out, right? Because the total surplus in the society will be
this add to this one, the P cancel out, right? It's the VI, right? If I get to the one who like the most, that is efficient, right? If you get it to the least efficient, that's not very good. The second one, the question is how to make sure that, okay, I maximize my profit. This is a different idea, right? It's the idea that I want to maximize my profit. It can be the case that there may be inefficient outcome, right? It can be the case where the object is not so. So later you see how to implement that is to, you will see you say second price auction with reserve price. Just like selling this, this the government sell the land. So you will say if the price is too low, I just keep it. Okay, that will be something like that. Okay. But I don't want to go further. Maybe this is the final remark, right? So how do we do under complete formation? Okay, it's very simple. If the seller knows everyone's, that's very simple. I just set the maximum, then I'm done deal, right? So the question which we'll discuss 2 weeks later, sorry, which will be going to design different rule so that everyone would try to tell the auctioneer what they want to pay. According to the rule, they would pay how to allocate. Okay, I'm sorry that I would have to take 2 weeks off, but we'll decide whether we need to make up. Okay, or we can make the exam, take home, then don't need to make up. Okay, maybe that may be more preferable. I don't know. We will decide 2 weeks later. Okay, so I have the assignment. Then you can try to do it for the game theory. Please do the assignment. Otherwise, you don't learn, right? So see you 2 weeks later time. And if you want, you can take more candy as you want. Okay, I see you.